When working with eigenvalues and eigenvectors, it's also useful to look at simple transformations or common transformations for the matrix and see what impact that has on our calculations for the eigenvalues and eigenvectors. So imagine considering a matrix A with eigenvalue lambda and a corresponding eigenvector v. So right away, you know that for this matrix, if you multiply it by v, you're going to get back the scaled version of v scaled by lambda. And why is that? Well, that's our eigenequation. That's the whole point of calling an eigenvalue and a vector appropriately. What we're going to do now is do 4 examples where we find the eigenvalue and corresponding eigenvector for some tweak to the matrix we already started with. So we start with matrix A, and we want to study now k times A. So we're going to study k times A, and specifically times v. So it's the same eigenvector, and we're just wondering, well, can I simplify this the same way I did up here, or does the k ruin things for me? Well, fortunately, it turns out nothing really changes because we can regroup this as k times A times v. That's just regrouping. And then A times v, we know, courtesy of the eigenvalue equation, is lambda times v, the same as lambda times v, the scaling of our vector. That's our eigenequation. And if I just write that out on the other side here, k times A, and let me write it one more time so I can highlight the blocks that I want to highlight. K lambda times v. So what we have here is a new matrix. And we didn't have to assume anything about v, except that it was an eigenvector of A. We were told that up front. When we scale the matrix by k, not too surprisingly, I guess, we get a new scaling factor. And so what we learned from this is that v was an eigenvector of A. It's also an eigenvector, or a vector that gets scaled by for ka. And with corresponding eigenvalue, so we know that the eigenvector is still an eigenvector. It's a direction that gets scaled, not rotated and anything else, just scaled. But the corresponding eigenvalue is different. It's now k times lambda. So if we scale the transform, we also scale the eigenvalue. And that actually makes total sense if we think about scaling as the procedure that we're looking for here, that v gets scaled when we do this transform by lambda. A scales v by lambda. It should not come as a huge shock that if we take all the elements of A and scale them by number k, it's going to scale v by k times as much, k times more than we had before. So we can go back to the geometry of these transformations and see if these results kind of make sense, and they do here. Let's take a look at a few more modifications we can make, or other related matrices to A. Specifically this time, we're asked to find an eigenvalue and corresponding eigenvector for the inverse matrix A inverse. So we know that A has an eigenvalue and corresponding eigenvector V. So we know as a result that A times that vector is the same as lambda times that vector. What we're going to do now is multiply on the left by A inverse. And you'll see what we get with that. So A inverse times AV is equal to A inverse times lambda V. And now we can regroup, we can take away these parentheses, and this A inverse times A, of course, the whole point of that is that they invert each other away and we get back to the identity transformation. So we get V, or I times V, or just V. And on this side, what we're going to do is bring the lambda out front. So we'll have lambda out front, A inverse times V. And we start looking at that and going, well, hey, I've got a matrix times V. Let me write that on the left-hand side. So I've got a matrix times V. If I do that what I could do is divide through by lambda. And then I just write it in a way with this on the right-hand side, because that's where we like to write it, because now we have our new matrix and we have our new scale, our new scaling factor. Oh look, when I take the inverse matrix and multiply it by v, I get the same vector back, but scaled by 1 over lambda. So v is also an eigenvector of A inverse. So if A has an eigenvector v, the inverse has the same eigenvector, but of course we're changing the eigenvalue again, just like we did last time, with corresponding eigenvalue 1 over lambda. And again, there's a really nice interpretation to this from the geometry. If we think about scalings and think about geometries there, A scales the vector v by lambda. Again, that's what we start with the eigenvalue definition. And A inverse, well, if A, say, scales my vector by 2, if I invert that, I have to undo the transformation on exactly the same place. Well, it's going to scale by 1/2. So in general, we're going to have a scaling by 1 over the original scaling, and that's going to be how we undo transformations. All right, let's do a couple more quick ones in the same vein. We've got a matrix A, eigenvalue lambda, corresponding eigenvector. Find the eigenvalue and corresponding eigenvector for a related matrix A plus Ci. Okay, so remember, we know that A times V is lambda times V. This time we're going to study A plus Ci times V. So this is what we're working with. What we can do is expand that out, I guess, to get something to work with. Again, we're trying to use this property here. We can't use it yet, but we can if we expand things out. So, because once we've expanded things, you can say, oh, A times V is one of the terms. We know that's lambda V. We also know that an identity matrix times V is the same thing. So we're going to get CV. And that, if we group, go the other way again, we have V in both of these. So we have lambda plus C times V. And what did we start with? We started with A plus Ci times V. So what's important here is not necessarily the relationship we're finding at the end. It's the process of starting with the known fact and using it to study something else of interest. Because what we just found is that we have a new matrix here, but we've shown that when we multiply that new matrix by V, we get, lo and behold, V again, but with a new scaling factor. So if we happen to take a matrix and add some multiple of the identity matrix to it, so we add things down the diagonal, we're going to get that V is still an eigenvector. So V was an eigenvector of A, but V is also an eigenvector of A plus Ci, this new matrix, with the corresponding eigenvalue. Eigenvalue of lambda, oh, we tweaked it though. We ended up adding a plus C. So lambda plus C. And last but not least in this list of demonstrations, same construction. We have a matrix A, we know some eigenvector and eigenvalue pairings, and now we're interested in A to the 10th power. And remember that this is matrix multiplication we're talking about here. So this is hard in general. It's hard or tedious to find the 10th power of a matrix. You have to do your rows times columns, all that work every single time we do one power. What we're going to see is that eigenvectors provide a way around that that is tremendously helpful. So AV lambda V, we know that already. What we're going to study is A to the 10th times V. Now the whole point of a to the 10th is that it's a times a, I'll put brackets here, times a times v. Let me put another one in there. So this happens 10 times. What we can do, though, is package that off. We can have 9 times these, and then just say, well, I'm going to calculate the a times v part. Why the a times v? Because that, through the eigenvector relationship, is lambda times v. So now we have a times a times a times a. This time it's only 9 occurrences, though. And we have our lambda v here. Well, guess what? We just do that over and over again. I have 9 things. I can go down to 8 a's and multiply one of these in, and I'll get lambda squared. And I think you can see the trend here. At the end of the day, we're going to get lambda to the 10 v's. So we started with a to the 10 times v, and we get a much simpler expression, lambda to the 10 times v, after we simplify. And so v is an eigenvector of a, but v is also an eigenvector of a to the 10 with corresponding eigenvalue of lambda to the 10. Now, I hope it's fairly obvious the 10 is not a magic thing here. We could have done 100, we could have done 1,000,000, we could have done 7. A to any power would have worked, and we would have gotten the multiplicative effect lambda to the power 10 instead. So if we have eigenvectors, we can do great things in simplifying this complicated expression. A to the 10 in general is a mess, it's a disaster. But if we multiply it by a specific vector, one of the eigenvectors of A, then it just becomes a scalar to the power 10, and that we can do in our sleep. That particular relationship is going to turn out to be surprisingly handy when we look at our big application problem for this week.